Hello everyone, welcome back to Year 11 Chemistry. Today we'll be discussing how to calculate oxidation numbers and how they relate to redox reactions. So as always in chemistry, we're going to start with a definition and then we can start building on to some applications. So a oxidation number is basically a number that's related to a change as a result of reduction or oxidation. As we've already talked about in our previous videos, reduction and oxidation are paired half reactions that occur within a full redox process. They are related to loss or gain of electrons. From our previous video, we discussed the definition of a transfer of electrons or a transfer of oxygen. So the oxidation number is basically building onto the definition of the transfer of electrons. The best way to understand what oxidation number is actually to learn the rules on how to calculate them and then looking at some examples. So the first rule for calculating an oxidation number is basically we look at the charge of a molecule. So when we have some elements paired by themselves, we look at the charge of the molecule. So we can see that the chlorine, the oxygen and the magnesium, they all neutral because we can see there is a charge missing on each of these molecules. So we know that the charge on these molecules is 0. So what that effectively means is there hasn't been a transfer of electrons, either by gaining electrons, so that would have a negative charge, or by losing electrons, so therefore that have a positive charge. Because there's been no net transfer of electrons thus far, we assign these molecules an oxidation number of 0, because they haven't had a net change in the amount of electrons per atom. So now we're going to have a look at the charge on an ion. So say if we have chloride, so say in some sodium chloride solution, say seawater, we would have free chlorides in solution. If we have hydrogen ions, same thing with dilute acids, you'd have free hydrogen ions, and then zinc ions in solution as well. So what these stand for with our single negative charge on our chloride, for example, is that each chloride ion in solution has effectively gained an electron from another atom. So it doesn't matter where it came from, we just know that each chloride has gained a single electron. So we actually assign the chloride with an oxidation number of -1. So you can see now from above we wrote our oxidation number in brackets here. Now we've got a sign. So we see that we had a -1 because we've gained a single negative charge in the form of an electron. We write the sign in front of the number and we also write it in brackets above the atom. So we're also going to go in the same fashion for the hydrogen ion as well. We've gained a single positive charge, so we've effectively lost a single electron. So now we have an oxidation number of +1. Now with our zinc, we have a charge of +2. And so in that sense, the zinc, each atom of zinc in solution, usually because zinc ions are in solution, we can see that we have lost 2 electrons to some other molecule or atom. So we would assign that zinc ion a +2 oxidation number. Okay. So what we're going to run into is basically molecules where we have multiple atoms inside the molecule, or the salt in this example. So basically what we use is our knowledge of the periodic table to assign oxidation numbers to atoms that we regularly encounter. So the first is group 1. So from our memory we know that group 1 lies on the left hand side of the periodic table. So what that means is, being in group 1, they have a single electron in their outermost shell. So these atoms really want to lose this single electron because then they'll have that stable full octet valence shell. So that's why we know that when lithium and sodium, for example, are linked with or bonded with another atom, we know to assign those atoms with a oxidation number of +1 because they are very regularly found to lose a single electron. So overall, each atom of lithium and sodium will have lost a single electron, so they would have a +1 oxidation number when paired in a compound. The second example is group 2. work in the exact same fashion. This time they have 2 electrons in their outermost shell that they would love to lose. So we would assign those a +2 oxidation number because we know they will regularly lose 2 electrons when paired with other atoms. Now, so another example that we know is always true when paired with other atoms is oxygen. So oxygen is assigned a -2 oxidation number. So you can see with the magnesium oxide, we see the magnesium has a +2 oxidation number. And we know from our knowledge that oxygen is in group 6 on the periodic table. It likes to gain 2 electrons to have a 4-octet shell. So the single exception of oxygen's oxidation number is when it's paired with peroxide. And there's a very good reason for this. It's to do with the chemistry of the peroxide bond. So when oxygen is paired with, for example, just water, you would see that the oxygen has basically gained the control of 2 electrons from the 2 hydrogens in water. So it would have usually a -2 oxidation number on that water. But if we have a peroxide, you'll see in the structure of peroxide, it actually shares a bond with another oxygen. So and they would share the electrons in that bond equally. So overall, per electron, it's only gained a single electron from from each hydrogen in that molecule. So when we're talking about our oxidation numbers, it's always per atom per atom inside each molecule. So in peroxide, because each oxygen inside that molecule has only gained the control of a single electron from each hydrogen, we would only assign the oxidation number of oxygen in peroxide as -1. So some other examples. So we've got hydrogen. In a very much similar case as the peroxide, the hydrogen likes to lose a single electron because it only has a single electron, and hasn't got a very strong control over that electron because of its low electronegativity. So it likes to lose that electron to other atoms. So you can see in the hydrochloric acid, it's assigned a +1. And again, in sulfur, hydrogen sulfide, it is +1 for each hydrogen. So you're going to notice if we have multiple atoms, say in the peroxide and the hydrogen sulfide, we write the oxidation number as just in terms of a single atom. So even though there are 2 hydrogens inside hydrogen peroxide, we only write the oxidation number per hydrogen. So instead of +2, because we've got 2 hydrogens there and they each have lost control of a single electron, we'll just assign it a +1 because it's always per atom, and this is very helpful later on, which we'll look at further. So now we're going to look at some more molecules and go into greater depth. So as we've already discussed, we've got water, and we know from our rules that hydrogen likes to have a +1 oxidation number inside a molecule, and oxygen likes to have a -2 oxidation number inside of a molecule. So our group 1, group 2, our hydrogen, our oxygen, and also our group 7 halides as well. We all know those oxidation numbers off by heart. They are always a given when inside a molecule, so we can just assign those straight away. But then we've got sulfur dioxide. The sulfur group 6, we actually don't know for certain what oxidation number it will have inside the molecule. So what we do is we assign the oxygen first as a -2. We know that because it's in group 6, so we like to assign the -2 oxidation number straight away. So the way we calculate the oxidation number for a molecule that is neutral, so no charge, is that the oxidation number, or the sum of those oxidation numbers in a molecule, has to equal 0. So if we know they have to equal 0, and the oxygens have a -2 oxidation number per oxygen, then to counteract that, we can actually make an equation. So you can either solve it in your head straight away, or you can make a little equation. Since you know the sulfur plus the oxidation number from the oxygen has to equal 0, we can form an equation like so. Then we just combine or multiply out the 2 and the -2 to get sulfur take 4 is equal to 0. Then we can rearrange to find the oxidation number of sulfur to be +4. So you can see that if we have two negative 2s in form of the oxidation number of the oxygen, we need a +4 oxidation number of sulfur to counteract that. Now we've got a sulfuric acid molecule here. In the same sense, we assign the oxidation numbers of the atoms we do know. So the sulfuric acid will be, or the hydrogen will be +1, and the oxygen will be -2. So you're going to see this in every example in terms of hydrogen and oxygen when in a molecule. Then we can form the exact same type of equation where we have two lots of a +1 oxidation number for hydrogen, we have a sulfur, and then we have four lots of -2 of the oxidation number for oxygen. Then we just expand just like before, simplify, and then solve for the sulfur to be +6. Now, so we're going to look at some examples of charged ions and how we calculate the oxidation number of atoms inside of those. So once again, we always start with our oxygens or our hydrogens, but we've only got oxygen here. We have four lots of this -2 oxidation number for oxygen, and we have a sulfur as well. But the only difference between ions and molecules is that the oxidation number of the ion has to equal the charge. So the charge was -2. So overall, the oxidation numbers have to sum to -2. So once again, we have sulfur plus four lots of a -2 oxidation number oxygen. So we just expand that out. So sulfur take 8 is equal to -2, rearranged to solve for the sulfur. In the much same fashion, we're going to solve for the carbon in this carbonate. Once again, we form an equation equal to the charge of the molecule or the ion. Then we expand out the negative, 3 take -2, and then solve for the carbon to get +4. And we write that above the atom. Final example with the single hydrogen phosphoric acid. We assign the +1 on the hydrogen and the -2 on the oxygen. Form an equation once again. The charge once again is -2 because of the charge on the phosphate part is the overall, is -2. Then we simplify down, solve for the phosphorus, and then we have a +5 on the phosphorus atom. So now we can apply the use of these calculations of oxidation numbers to redox reactions. So the definitions here is that a oxidation half reaction will see an increase in an oxidation number of a particular atom, and the reduction will be a decrease in oxidation number of a particular atom. So what we're going to do is see a few examples. So we see this equation here with copper reacting with silver single positive ions to give copper ions and solid silver. So we follow the same steps as before. So we see that we have some molecules. So we've got copper, metal, and silver by themselves, which we would assign 0. So we've shown the copper. And the silver ions have a single positive charge per silver atom. So we would say the oxidation number for each silver is a +1. Once again, that's because each silver atom has lost a single electron, giving it a +1 oxidation number. Copper works in the exact same way with 2 positive charge. And once again, silver atoms being neutral and only being silver, it has to be an oxidation number of 0. So, using our definition, we know that a change in oxidation number, if that occurs, there is going to be a redox reaction, because there's going to be a oxidation half reaction, which we see is actually with the copper. So we can actually link together the copper atoms here. So we can see that copper's gone from 0 to +2, so that would be a oxidation half reaction. And then the silver has actually decreased with a +1 going to a 0 oxidation number. So that would be the reduction half reaction. Okay, so we're going to see another example here. So here's an example of a classic acid-base reaction, with the acid being hydrochloric acid and water being the base. So now we're going to assign the oxidation numbers of the atoms we do know. So we're going to start with hydrogen. Each hydrogen is going to be +1 because they are all found in a molecule. Then we can start with our, go on with our oxygen. So once again, we assign -2 oxidation number to our oxygen. And then the chloride, in both forms, has a -1 oxidation number because it's in that group 7. So you're going to see here that there is actually no change in oxidation number. So therefore, this reaction is not a redox reaction because 1, there are no oxidation half reactions and there's no redox half reactions, reduction half reactions. So overall, there is this reaction is not a redox process or a redox reaction. So now I'll pause the video and try a few examples of assigning oxidation numbers to the green species in the box below. Okay, so if you've had a go at all the questions here, we are going to show the solutions for all of them now. Okay, so once again, if you've had a bit of trouble or your answers don't match the solutions, then go back, re-watch the part about assigning oxidation numbers to atoms inside molecules and ions, and hopefully that will help you out. So now we're going to practice applying our oxidation number theory to full reactions. So pause the video, have a go at assigning the oxidation numbers and determining which atoms are being oxidized and reduced, showing the link between the reactant and the product atom. And then I'll go through the solutions. Okay, so we're going to start by balancing this reaction. So we can see that the bromide and the chloride aren't balanced with their particular partners on the opposite side of the reaction. So we want to balance by multiplying the coefficient of those atoms by 2, and then we can start applying some oxidation numbers. So we apply oxidation numbers to the chlorine and the bromine. They are neutral molecules with only one type of molecule present. So they automatically get assigned an oxidation number of 0 because there's been no net transfer of electrons for that atom in that state. Then we've got the bromide and the chloride. Once again, they have a single negative charge on the atom. So, and there's only one type of atom present, so we assign those with oxidation numbers of -1. Then we can link together the reduction and oxidation half reactant and product pairs. Then we can see the chlorine has been reduced to the chloride because there's been a decrease in the oxidation number. And in the exact opposite way, the bromide has been oxidized because it has gone from a -1 oxidation number to a 0 oxidation number. So it's actually increased in oxidation number. Then we will see that we have magnesium reacting with water. So we'll start with the balancing of the full reaction. So if we balance by multiplying the coefficient of water by 2, we can see that we balance for hydrogen, so 4 on that side, 4 on this side, and then 2 lots of oxygen on each side. So we're fully balanced, we can start assigning oxidation numbers. So we assign oxidation numbers to the components where there is only a single type of atom and they are both neutral. So we assign those with an oxidation number of 0. Now we're going to assign the hydrogens and oxygens throughout the whole reaction, and that actually finishes our water with -2 and +1 on the oxygen and hydrogen respectively. Now, so this is a little complicated here. We actually have a magnesium hydroxide, which is almost like a form of salt. So we've got overall a negative single charge per hydroxide. We don't show it like this, but that's what's happening in our minds. And we have 2 lots of those single negative charge hydroxides. And we're balancing out with a single magnesium atom. So that tells us that we're expecting a +2 charge on the magnesium. So that's how we actually calculate the oxidation number of the magnesium, just using that fact there. Okay, then we can link together the atoms that have been reduced and oxidized, so showing the reduction of the hydrogen this time with a +1 oxidation number beforehand, going to a 0 oxidation number afterwards. So you're going to see that only 2 atoms of the hydrogen have actually been reduced. So not all of the atoms on the reactant side have to undergo a redox process. So only the hydrogens found in the hydrogen gas, or the dihydrogen species here, have actually gone through reduction. Now the magnesium here, just a single magnesium to a single magnesium, much more simple. It's gone from a 0 to a +2 oxidation number. It's gained oxidation number, so therefore it has been oxidized. And we just show it again, linking the atoms. Now we're going to have a look at this sulfur reaction here, a lot of sulfur going on. So this time we've got two lots of sulfur on the left hand side, and on the right hand side we've got one species containing sulfur. So we're going to see an example of that now. So we balance the equation first, we multiply out the coefficients to make it fully balanced, and we're going to start assigning oxidation numbers. So sulfur is the only compound where there's only one atom in that molecule, so we can assign that 0 because it's got a neutral charge, no charge. And then we can start assigning our hydrogen and oxygen just throughout the total reaction. So there's only one atom that we have to calculate the oxidation number for. Two lots of -2 on the oxygen. To counteract that, to give a neutral charge, due to the neutral charge, we need a +4 on the sulfur. And we also have a counteracting of the two lots of +1 hydrogen with a -2 on the sulfur. Now we can show the oxidation and reduction linking with sulfur from the hydrogen sulfide being showing an increase in the oxidation number from -2 to 0. So that is the oxidation component of this redox reaction. And we've also seen the sulfur go from +4 on the left-hand side to 0 on the right-hand side. So that would be the reduction component of this redox reaction. So thanks again for listening to Year 11 Chemistry. So for the next video, we're going to be talking about balancing and combining redox half equations. Thank you for listening. Don't forget to like and subscribe.